And hi, welcome to this video on basic physics. I'm making this because I know someone who is going through exams soon and then needs some help with explanation because not getting kinematics, not getting proper understanding from the teacher. So I'm trying my best to do something to help with that. So it's just nice. I'm going to post this on YouTube so that anyone who wants to know can benefit. Okay, so yeah, thanks for coming. I will just start us off basically why learn kinematics. So this is from Dr. Ong. Yes, I have a PhD now, but yes, I think it's good to pass on the knowledge to the next generation, hopefully inspire more interest in physics, and for me personally, nuclear science and engineering. Okay, so let's start with kinematics. Why bother learning kinematics? What is kinematics about? Okay, kinematics is about studying how objects move from point A to point B. That is a very layman way of saying it. Okay, I hope the volume's loud enough. Okay, volume should be loud enough. Okay, but this picture is kind of boring. Okay, let's contextualize this. Meaning to say, let's put this in a real life situation. So I come from Singapore. Okay, Singapore is a very small island. It's a sort of a diamond-shaped island. Okay, and they like to call Singapore the little red dot. Okay, and one of the favorite pastimes of Singaporeans is to travel from one of the world's best ranked airports called Changi Airport, and a lot of my fellow Singaporeans like to travel to this place called Japan. Okay, so you want to go there on holidays, and then you go to this place called Japan, and Japan is going to be shaped like this angled not L but and you're going to land up somewhere over here, which could be, if my geography does not fail me, this may be around Tokyo Narita, or I think there are two airports down there, Narita and Haneda or something like that. You guys have AI. I'm going to assume you have AI, Google, whatever at your hands. So just go and check me out, fact check me, do whatever you need to do. Yeah. So that's the baseline for all my lectures or sharings on physics or any of these topics. So just have AI on standby. Make sure you learn, use all the tools available. I will assume you have them, and I want you to do the due diligence, meaning to say search it yourself. Okay, make sure you internalize your learning. Okay, so how long does it take to go from Changi Airport in Singapore to Narita Airport in Tokyo? Okay, most of the time it takes around 8 hours. Okay, and why is this important? Why is this 8 hours important? Because you as a traveler want to know how long you are going to travel. So you might want to prepare some things for yourselves, which could be, I don't know, snacks, but I think the airline will give you snacks, or maybe you want to bring some pillows or whatever helps you sleep on the plane, or you want to watch some movies. Okay, for the traveler, this 8 hours is important to know. Okay, so know how much discomfort or comfort to prepare for. Okay, and of course that will factor into the cost. Okay, why is it expensive? Because the longer you fly, the more fuel you need. Okay, and for the airline, fuel is not just a matter of money. The fuel is a matter of safety as well, because you need to ensure you have enough fuel to fly from one airport to another. So the longer you fly, the more fuel you will need. Okay, and of course the bigger your fuel tanks need to be, so on and so forth. So how do you get this 8 hours? Okay, this 8 hours comes back to kinematics. Okay, so it talks about how fast an object travels from A to B, and that will have all these consequences I talked about. So this is why it's important to study kinematics. Now, in a plane, right, there are a few stages. Okay, let's say this is Changi and this is Narita. Of course, nothing of this is to scale. I don't represent Changi Airport Group or the Singapore government or the Japanese government or whatever. No, I am doing this just for educational purposes. Okay, but okay, I'm also not an aviation engineer. Okay, I am a chemical and nuclear engineer, so I know some basic principles, but I'm not an aerospace person. But nevertheless, some of these principles are still the same in terms of physics, the underlying principles. So, Changi Airport, you have your plane. This is a very poorly drawn plane with an oversized tail. Okay, so this plane is going to need to take off. Okay, so it needs a runway, right? This is a runway. So this runway, this plane's got to speed up on the runway. It's going to start maybe somewhere here, and this runway has to be long enough for the plane to take off. Okay, and I know at Changi Airport there are actually trees around the back, so you do not want the plane crashing into the trees, or else you get some major aviation disaster. Likewise at Narita, I can't remember exactly, okay, what the airport looks like because I don't travel there often enough. But as with every airport, there needs to be a runway to land. So when the plane lands, it's going to be going at some very fast speed, okay, or velocity, in, I don't know, maybe 250 meters per second or slower. 250 is pretty fast. You're almost at the speed of sound. This is maybe the speed in the air. Maybe that's too fast. Maybe I'll just put 100. Okay, I don't actually have the numbers off the top of my head, so again, you guys have AI, go and search it yourself. Okay, so it's going at this speed and it needs to slow down to a stop before it hits the end of the runway, right? So because at the end of the runway there are probably going to be buildings or going to be trees, or even worse, it can drop off right into the ocean. Some airports are like that. Okay, so how long does your runway need to be? How long does your runway need to be? Okay, all this, again, we come back to kinematics. We need to study how fast an object can accelerate or decelerate so that you don't crash your plane into the tree. That's the idea. Okay, so this is just the takeoff and landing stage. Takeoff, landing. My handwriting is not good, unacceptable, even though I'm a doctor. Technically, I can use that as an excuse to have lousy handwriting, but I'll try not to. Okay, so I'll try to have this legible as possible. And oh, by the way, all these notes will be on GitHub. I will leave the link in the description. Now I'll probably show it in the video, this video or the next video. Okay. So these are just two stages: the takeoff and landing. Then after you leave this runway, you have ascent. Okay, which means the plane is climbing. Okay, I don't know if I'm using the correct aviation terms. So the proper aviation crew, pilots, air crew, they'll probably correct me on this. But if you are already working and all that, you probably won't watch this video anyway. So, but yeah, just correct me on this in the comments if I'm messing anything up. Okay, so after takeoff, you have the ascent until you reach cruising altitude. Okay, altitude is just a fancy word for, I guess, height. Okay, you'll go on cruising altitude where the plane kind of goes on autopilot for very long, maybe 6 hours. The takeoff and landing, maybe they'll take 1 hour each. Okay, takeoff, ascent, and okay, after a cruise, you start your descent, which means you decrease your height. So this is the opposite of ascent. Okay, and then you probably need to take some time, and then you kind of ease the plane into landing. So this is the whole how the plane takes off and lands. Okay, all this is very important to study kinematics. It's important to study kinematics because you want to understand how long a time you need for the plane to ascend and descend, how much space, how much airspace do you need for the plane to circle. Of course, there are other factors other than kinematics that, like, you know, there's air traffic control and you don't want one plane to crash into another, or so on and so forth. These are other reasons why a plane may not take the most direct path. But if the plane takes a curved path, you're going to need a certain amount of airspace. So you probably need some airspace in the air to do this ascent and descent cycle. Again, that airspace dimension is going to be determined partially by kinematics as well. So I hope this gives you good reason into why you want to study, or why you should study kinematics, and not just have formulas randomly placed at the back of your head. Okay, so that you're just using it blindly, not blindly, how to say, using it without context would be the better way to express it. Okay, so I hope this picture gives you reason why someone might study kinematics. Okay, so I'm going to use this 5 stages: the takeoff, ascent, cruising, descent, and then landing. I'm going to use this maybe as a way to sort of structure problems. Okay, so let's say, okay, cruising. That's the first one. Let's talk about cruising. Okay, cruising. Cruising is a very easy problem to solve because the plane is in the air and you'll just go from point A to point B at roughly constant speed. Okay, so let's say point A to point B. So this is not the airport itself, because you see the airport itself is on the ground. The point A to point B I'm talking about is in the air. Okay, so this is the point A to point B. So roughly constant speed. Okay, roughly constant speed. Alright, so let's go back to our poorly drawn map of Singapore to Tokyo. Okay, you're roughly heading northeast. Okay, you're heading northeast. Okay, in fact, Singapore and Tokyo has a 1 hour time difference if I'm not wrong. Okay, so you're heading northeast or northeast if you want to be so precise. I don't know what the coordinates are. Again, you guys have AI, Google, go and search, correct me in the comments. Okay, so yeah. So you want to be headed from point A somewhere in the air to point B somewhere in the air. Okay, how do you get from point A to point B? How much time do you need? Okay, so in this situation I want to introduce you to the idea of vectors. Okay, because yes, you want to be traveling from point A to point B, preferably as in the most direct path as possible, because if you point yourself in the other direction and you start flying all over the place, you might not have enough fuel to make it to Tokyo and your plane will crash. So that's not a good thing. So in kinematics, vectors are important. Okay, vectors are important. So it's not just the speed, but the direction. So what are vectors anyway? Vectors, you might have heard it in physics class. These are called quantities. Quantities. Okay, Quantities. Okay, quantities with magnitude. That means how big. And direction. So to travel from Changi Airport to Narita Airport within these 8 hours, you have to consider how fast you're going. Not only that, you have to consider where you're going. So that's why vectors are important, or else your plane will crash. Okay, you obviously want to travel point A to point B in the air. Okay, like what, 800 kilometer an hour in this straight direction, and you don't want to have 800 kilometer an hour going into the ground, right? Or into the ocean. You will crash your plane. So that's why vectors are important. Okay, so this is not the velocity we want. This is the velocity we want. It's a safety thing. Okay, so this is why we want to study kinematics using vectors. Okay, especially for aviation, or even for driving, all of these are safety issues. Okay, so you want to point your plane, point your car in the right direction. Okay, so again, I want to emphasize vectors are important. Okay, so vectors are important. Right, so you want to be traveling preferably in this direction, okay, from A to B. You don't want to travel here, you don't want to travel into the ground, you don't want to travel into outer space where there's no oxygen for your jet engines, and then you'll probably crash the plane anyway. So yeah, point A to point B, okay. So even with this cruising, you want to make sure your plane is roughly level. Give yourself a nice flight experience, okay, so you don't crash into the ground, you don't have a bumpy ride, so on and so forth. Maybe you want to avoid turbulent weather as well. Yeah, so that's what we want to do with cruising. Okay, so cruising roughly constant speed is the most straightforward. Okay, so let's say from here to here, I'm just pulling numbers out of my head. Maybe it's 2000 okay, more 4,000 kilometers. Okay, maybe 3,005 kilometers from this point A to point B in the air. Again, I'm pulling random numbers out. You have AI go and search the real numbers. You can redo the problem like this. So 3,500 kilometers, okay, from point A to point B. I'm asking the most obvious question here. And your speed is what, 700 kilometers an hour? This is a typical cruising speed, which or could be 800 plus kilometers an hour as well, 700 to 800. Okay, I say I know this because I've been on enough flights to look at the flight data, and this is roughly how it is. Okay, how long will it take to get from point A to point B? Let's say the 700 kilometer an hour case. Now this is simple. Your speed or velocity, if you don't want to consider direction, because well, I'll say point A to point B is just a straight line. Okay, I'll say point A to point B is a straight line. That's the simplest case, right? So what's the velocity? Velocity is distance over time. Okay, so you want to calculate the time taken, right? Time taken. So you bring the time over and you divide both sides by velocity. Okay, you switch these two. So it's distance over velocity. So what's the distance? Distance 3,005 over 700. Okay, 3,005 over 700. 3,005 over 700. Yeah, that's your number. But 3,005 over 700, that will be 5. Okay, but 5 what? Okay, so I want you to have this habit of putting your units there. Is important because actually even the NASA engineers, when they use a wrong unit, they actually crash a $1 billion probe, or a probe costing a few hundred million. Again, that was a very famous case because they used the wrong units. One was in imperial units where they use pounds and everything like that. Then the other unit system was the SI units. Or there are many unit systems. Basically, they used the wrong one and they crashed their probe, wasting millions of dollars. Okay, again, AI, Google, go and check me out, whatever. Not check me out, check what I'm saying out. So just yeah, this is the moral of the story. Even the simple things like units, you make one mistake in real life, it costs you a lot of money. And if this happens in a plane, it can be okay, never mind. I will not go there. Okay, so let's say 3,500 kilometer, 700 kilometer an hour. So the hour is in the denominator. So when you divide 1 over hour, you get the hour in the numerator. So that's 5 hours. This is a piece of cake. Okay, no need to do much. Okay, don't need to do much. Right. So this is the most simple case. We will use the formula V equals to ST, or rather S equals to VT. Okay, this V is velocity, S is displacement. Displacement is the vector form of distance. Okay, distance is a scalar. Scalar only has magnitude. Displacement is a vector. Likewise, velocity is a vector. Velocity is a vector, but speed is a scalar. Okay, both of them have the same units, but velocity has direction. So v is velocity. Okay, now this is the simplest case. We don't even see what use vectors has because the velocity and the speed is all going in the same direction. So yeah, this kind of is pointless to not say pointless. It seems pointless to talk about vectors. Let's give you a bit more realistic case. Let's say from A to B is still 3,500 kilometers. 3,500 kilometers. Okay, but the most straightforward path here may not be the best case. Maybe over here you have turbulence. Okay, you have turbulence. So what you need to do? You have to make a detour. So your actual path may be something like this. Okay, I'll give you a simple path like this. Let's say you go to C and then you go up to B. Okay, so this is a very common thing to do. You might want to avoid turbulence, or some places, or for some other reason, you might want to avoid the straightest path possible. Okay, so again, yes, I should take my own advice, and I do forget sometimes, but I'm saying it, okay, for your benefit. Please put the units there as far as possible. Okay, so now at cruising altitude again. Okay, again you have the shortest distance, 3,500 kilometers, but now you have this thing you want to avoid. It could be turbulence, it could be something else, and then now you have to take this detour. Okay, detour. So now direction becomes important, because now you're talking about detour. Direction becomes important. Okay, so let's the easiest way to sort of represent this direction is using this XY graph in 2D. Okay, so this is the Y direction, this is the X direction. Let's say I have A, I have B, and then this is 3,500 kilometers. Okay, let's say I have C here, and that's the actual path you travel because you're taking a detour. Okay, so yeah, what now? Okay, looks like you need to do some kind of trigonometry. Okay, so oops, yeah, that's where a lot of math comes in, and you realize a lot of physics needs this kind of math. Anyway, yeah, so yeah, I needed a break, so I stopped recording and I just come back. Anyway, yeah, let's say you have this situation. Okay, let's say you have this situation, and then you want to go from A to C and going to B. Okay, how long does it take? Okay, of course there isn't enough information to solve the problem, so let's make some assumptions. I'm just making numbers up just for the sake of demonstration purposes. Okay. So let's say you have this triangle here and then you can draw a right angle triangle. It is very, very common. You use right angle triangle in this so-called doing vectors. So your sine, cosine, tangent actually becomes important. Trigonometry. Okay. So this is and I'm not gonna teach trigonometry to you. You got to go and get it done yourself. Okay, do go and search AI, do whatever. Okay, so I'm going to say this is what, 800 kilometers from here to here. Okay, should I? Yeah, I'm wondering, should I teach trigonometry? Okay, go and learn it from AI. Do whatever you need to do. Copy paste formulas. I'm not going to teach it because I just want to get the concept. Okay. So this one, because this is a slightly more complex situation. Okay, so let's say this, if you have a right angle triangle between A and B, you have this 800 km side down here. Okay, so and let's say going from, let's calculate how long this side is first. you will need to use Pythagoras theorem. Okay, so and let's call this point D. Let's call this point D just for the sake of convenience. So what is AD? Okay, length AD. Okay, so I'm going to use LibreOffice Calc. Okay, to do my calculations. So so you can use Excel or what. It actually functions well as a calculator. I'm just going to zoom it all the way in like that. Right. Okay, zooming all the way in. Zooming all the way in. And let's do some basic Pythagoras theorem, which again I want you to go and search it up. So this is the hypotenuse 3500 square, and if I want AD square, I will need to do minus 800 square. Both of these are in kilometers. I'm not going to put units here, and this is your answer. So I'll need to write this based on Pythagoras theorem. Okay, let's again put this AD. Okay, equals, you need to actually do this. 3500 squared minus 800 squared. So that's Pythagoras theorem. I don't know why it's such a nice round number. Oh wait. Yeah, I guess when you square it, it's a nice round number. But when you start square rooting the thing, then it's going to be a very ugly number. But let's do this. I'll need to square root this. Square root. Okay, this number. 3407 km. Okay. Now, another good habit to have is be very mindful of how many significant figures you have. This is 5 significant figures. Okay. So for this 800, anything with a 0 is a bit harder to determine significant figures, but this at least or at most is 3 significant figures. Okay, 3 significant figures. And the 3500 at most is 4 significant figures. And we do things like that because we want to take note of accuracy. We don't want to make the number so precise. Okay. Okay. So normally when we have final answer, we kind of take cue from the significant figures, but I can't remember the exact rules for this. It's something, okay, it's not very, very interesting, but yeah, it's important to know. Like when you're more refined, I have to go and revise and look for Google. I need to refresh my memory. But okay, generally speaking, don't leave too many significant figures. But when you're doing calculations, then leave more significant figures. So this is 5 significant figures which you should use as the intermediate calculation step. Okay, so AD, let's say this is 3407.3 km. Okay, and let's say AC is equals to 3000 kilometer, for example. Okay, so if you want to calculate the time, okay, AC is 3000 kilometer, then you need to calculate the distance between B and C. So what is BC? Okay, so I'm just giving you a flavor of what doing math is like with vectors. Because with vectors, you will have lots of triangles to deal with. Okay, when you place it on a X and Y graph like that, you are going to be able to see things a lot better with these vectors. Okay, so with BC, how do you calculate this length? Okay, so we calculate it using again trigonometry and the Pythagoras theorem. So this side is 800 kilometer, this side is about 407 if you just minus off 3000. So BC should be, okay, again square root of what? Okay, 407.3 square plus 800 square. Okay, so let's use Pythagoras theorem and then Pythagoras theorem and then solve our problem. So this one I will just minus 3000 first, and then I will have this number squared plus 800 squared. And what's this number? 805929. I'll just put this here, 805929, and I'll square root this. Okay, 897.7 km. Okay, that's BC. So I'll take away this. Now this is known. BC is 897.7. Again, if I make careless mistakes or anything, just let me know in the comments. Then I see what I can do to rectify. Meaning to say I can correct them later. Yeah, but this is roughly how you can figure out the distance between A and B, but you go and use a detour. Okay, so let's see AC and then BC. What's the distance, total distance? So AB plus BC. Okay, AB is what? AB is 3000 kilometers. Okay, I said, or rather AC is 3000 kilometers. AC is 3000 kilometer. Plus BC we just calculated 897, right? 897. Yeah. 3897. This one no need the calculator, you can also do. Okay, and again, I'm not even following my own advice. I should be putting kilometer here. Yeah, but it's totally understandable if you don't do it in the working, but it's beneficial for you. Yeah, even here I don't do, but I say as far as possible, right? But of course, I know during exams, you may not always have the time. So I guess what I can suggest is you just bracket this whole thing and then you put the units down here. If you want to go for a middle spot, or maybe put it like this: BC in km at the beginning. At least you specify the units somewhere. Okay. I know this is not exactly the standard way of doing it, especially in exams. You want to leave it at the final answer, but at least leaving it here, you will tell yourself that okay, these numbers are all in kilometers. Okay, just leave it somewhere. Just make sure you know somewhere. Okay, so 3897 kilometer, and how much longer will you take? Okay, that's probably your next question, because then you will need to see, okay, with this detour, how much more time, how much more fuel roughly. I'm not going to have you calculate fuel and all that. How much more time you need. So let's see. We have 3500 kilometer, and this is the detour route. So the extra time taken. Okay. I will just write this. Okay, so longer time, 397.7 minus 3500, and what's the speed? 700 kilometers an hour. I will just assume it's 700 kilometers an hour. Okay, so let's calculate. This one plus 3000 minus 3500. Okay, and then I divide by 700. Okay, 0.568. Okay, 0.568 hours. Okay, maybe I'll put 5682, and then I will maybe roughly calculate how many minutes. 34.1 minute. So if you have this sort of detour, it take maybe half an hour longer. Example. Okay, took half an hour longer to go from A to B. About half hour longer to get from A to B. Okay, these are just questions you might ask in this kind of flight scenario. So going from A to B, okay, this is important. I want to use this as an example to demonstrate vectors. Okay, I want you to use this example to demonstrate vectors. Okay, so A to B, right? A to B. The straight line distance between them is 3500 kilometer. Okay. straight line distance. So what is the displacement? What is the displacement? What is displacement from A to B? Capital A to B. Okay, displacement is how far, basically how far are you from your original placing. Okay, so the answer, yes, of course, 3,500 kilometers, but 3,500 kilometers how? Okay, so there are two ways you can actually signify direction, I guess. One is that you use this angle here. Okay, and how do you find this angle? Again, you have to use trigonometry. Okay, we know, I just said just now, the far side, the end side is 800 kilometer. Okay, 800 kilometer. How do you find this angle? Okay, we use trigonometry. Basically, it's using the sine theta. Okay, this is trigonometry. Okay, sine theta equals to opposite over hypotenuse in this right angle triangle. Okay, so right angle triangle here. This is the assumption. So sine theta equals to what? 800 over 3500. Okay, so theta equals to arc sine, a sine 800 over 3500. Okay, the other, I think you can put a sine or arc sine. The common way is to use the sine inverse, but I prefer arc sine personally, because in programming we use a sine a lot more than this sine inverse. Okay. Anyway, how do we calculate this angle? So, see, even here programming, it use a sine. Okay, arc sine. Okay, 800 divided by 3500. Okay, normally in programming like this, we often have our answer in radians. Okay, 0.2306 radian with respect to positive. Let's say you put this graph down here, because it's very important to draw graph, then at least you have some reference with respect to the positive x-axis in the positive x direction. So I will say with respect to positive x direction. Okay, so when you have your magnitude here, okay, and your direction, you will have your displacement. So that's a vector example. Now, again, vector is important because going from A to B, there's a certain displacement, but the distance you travel from A to B may be different. Like just now, there may be a detour that you make for whatever safety reason, or you might choose to, or some other aviation reason, you might choose to take this kind of detour. Okay, so your distance is traveled tends to be longer than your how do you call this? Than your total displacement. Okay, so yeah. So this is one way of representing your vectors. Okay, if you want to change this to degree, you just multiply by 180 divided by pi, which can be 3.14, but I'll just use the pi here in LibreOffice. This is 13.21 degrees. Okay, so theta is also 13.21 degrees. Okay, but programming is more common to leave it in radians, so I'll just leave it in radians. Okay. Now that's one way of representing vectors. Okay, this is a very foundation. One way of representing vectors is to use this 3,500 and you place this angle. Now the other way of representing vectors, method 2 of representing vectors, okay, which is more common if you go into more advanced level. Method 1 of representing vectors, okay, it's like this. You have a magnitude and direction, which is this angle. Second way, method 2, which I think I'm more comfortable with. Okay, use coordinates. Okay, coordinates. So what do I mean by coordinates? Okay, so this is very, very common to encounter in engineering. So let's say you go this much in the, let's say you go from A to D, this much in the X direction, okay? And then you go B to D, this much in the Y direction, okay? So you will actually split up this vector. We call this resolution of vectors, but it's basically splitting up this vector into AD, what we call X component. How far are you moving in the X direction, and then the Y component. How far are you moving in the Y direction? So the displacement vector, which we call S, okay, and sometimes vectors we like to put the arrow on top, okay. What we can represent in 2D, this is in 2D, is you separate it into how far you move in the X direction and how far you move in the Y direction. So how do you find this X and Y? You need to use trigonometry again. So how far are you moving in the X direction? Okay, how far are you moving in the X direction? Okay, you can use the Pythagoras theorem here to solve that, and we did use it just now. That is the distance AD. Okay, the distance AD is 3 kilometers. 3407.3 kilometers. Okay, so maybe I can write like this, where Sx equals to 3407.3 km, Sy equals to 800 km. Okay, and that's how you represent your vectors. Okay, now I mentioned trigonometry just now. Okay, I mentioned trigonometry just now. So how do you use trigonometry to get this number, 3407.3? So let's say I have the 3500 km again. Okay, I have this angle here, which is 0.2306 radian, which is this thing here. This theta here is 0.2306. Okay, and again, this is a right angle triangle. Okay, with vector math, there's a lot of right angle triangle. Okay, so how do you get this distance? Okay, we use cosine. Okay, so we just now it's AD, right? AD equals to, okay, the cosine formula is adjacent side, which is AD in this case, over hypotenuse. Okay, so AD, which is the adjacent side, how you calculate this length is to take the hypotenuse times cosine theta. Okay, 3500 times cos 0.2306 radian. Okay, again, good to have your units. So I can show you how to reproduce this number. Okay, 3500 times cosine of this thing here, 3407, almost there. Okay, 7.3. Okay, that will give you your kilometers. For BD here, again, you use trigonometry. You can do it as well. So instead of cosine, we have sine times sine 0.2306 radian. Okay, equal 3500 times sine of 0.2306 radian. You get 800. Okay, so that's how you find your AD/BD using trigonometry. Of course, you can use the Pythagoras theorem that I did just now. You need to have both of these tools in your toolbox. Okay, so this is the very much more common way we represent vectors. Okay, not just using this angle. This one's a lot easier to work with. Okay, so this is something I want to highlight. Now, I don't know if O level does this, but this is very common in A levels. So I didn't get used to this formatting, this style. But yeah, I want to introduce this so that you know the math later, that it becomes a little bit easier. Okay, so I think that's all. Because I talk about vectors and in the context of this air traffic travel. Now, of course, want to do something later called vector addition, some vector algebra, but later. Yeah. So that's what I want to cover today. Hope this was helpful in getting you more interested in why you must learn kinematics, or why people learn kinematics. You may not do it. Yeah. So hey, that's all.